we can take a closer look at both expressions. The expression for the maximum current amplitude, and the correction for the expression for the phase angle. You know, besides R, L, and C, I maximum, the amplitude of the current, depends on omega. Okay, it depends on omega, and we can plot qualitatively. We can plot how I maximum changes as omega changes. Okay, so here's I maximum, the resultant amplitude of the current, and here is how it depends on omega. Now, what if I have a very, very large value of omega? If omega is very large, then this term dominates in the denominator. Okay, so and that would tend to bring I maximum down to 0. On the other hand, if omega is very, very small, okay, if omega is very, very small, then that term dominates, right? That term really dominates, and it's also very, very large. So overall, V maximum would also go down to 0. So you see, either for very large or very small omega, I maximum really goes to 0. So you start from 0, you end up at 0, so you rise in the middle. Okay, it's like this, right? It's like this, and there is a peak value. For a certain value of omega, we call it omega naught, at that frequency. Okay. See, I maximum goes up from 0 and goes down to 0, but it reaches a maximum value at a certain frequency, omega naught. What is that frequency equal to? Well, we can easily get that from this expression. You see here, the only omega dependent part is here. Somewhere in a new denominator, we try to minimize this in order to get a peak value of I maximum. Okay, and that happens, therefore, when you set this quantity to be what? Well, don't forget there is a square, so the worst thing you can do to it, as small as possible, is to make it 0, right? Okay, so at omega equals omega naught, we have omega L minus 1 over omega C equals 0, right? I mean, you make this equal to 0. That makes the denominator as small as possible. So I maximum will be the greatest value. So omega naught and omega naught. And you can solve for it, and you find something that you're familiar with already. Omega naught equals 1 over the square root of LC. Okay, now does that sound familiar? 1 over the square root of LC. Where did we learn that? That was the frequency of what? The frequency of a pure LC circuit without any resistance. Okay, at that moment, with that frequency, you find you have a peak value. What is that peak value equal to, by the way? This term is already equal to 0. So V maximum over the square root of R squared is just simply V maximum over R. Now that sounds really, really simple, V maximum over R. What is that? That would be the amplitude of the current if there were no L and no C at all. Okay? Right? It's just, V maximum equals I maximum times R, and that's how you get I maximum. So it appears that at that frequency, it's as if the resistor is the only element in the circuit, while the inductor and the capacitor somehow disappear from the view. How does that make sense? Well, as a matter of fact, it makes good sense. If you go back to this phasor diagram, okay, this is always the key, the phasor diagram. You know that if omega is very large, then VL is very long, because VL goes like goes like omega. On the other hand, VC will be very short because it goes like 1 over omega, right? Gradually, as you decrease the frequency, you find that VL gets shorter and VC gets longer. And at some point, VL and VC have the same length, right? Now, if they have the same length, then when you add them together, what happens? They disappear, right? There is only one V left, and that's VR. And that VR should be equal to V. When at that particular frequency, you find phi has to equal what? 0, right? Because V, the EMF, and VR should be the same thing. It's, VL and VC totally cancel each other out. They have the same magnitude, but exactly the opposite phase, or 180 degrees out of phase with each other. They always cancel out each other. We call this particular circuit a purely resistive circuit. That happens only when VL equals VC. Okay, so I'm going to write a special case. VL, you compare with VC. If VL equals VC, we say it's you only have the resistor left, therefore we call it resistive circuit. Resistive circuit. And that happens when omega L equals 1 over omega C, or omega naught L, and then omega equals omega naught, 1 over the square root of LC. Okay, now, so at that frequency, you find that these two vectors, VL and VC, have the same length. So VL minus VC equals 0. Any frequency above that, VL would be longer than VC, so we say it's inductive. Okay? So, on that side of the graph, all the way from omega naught to infinity, the frequency is higher than omega naught, we say VL is longer or is greater in magnitude than VC. Okay, so the inductor overpowers the capacitor, is more important than capacitor, we say it's inductive. On the other hand, if the frequency drops below omega naught, then you'll find that VC is now greater in magnitude than VL. Okay, and so the capacitor is more important than inductor. What do we call it? We naturally call it what? Capacitive. Okay, it's a capacitive circuit. And right in the middle, between the two cases, we have what? A resistive circuit, or purely resistive circuit. It doesn't mean L and C disappear. It's just VL and VC just happen to cancel each other out at that point. If they cancel each other out, then the EMF is 100% borne by the resistor. That, of course, causes the greatest possible current. Okay, because you don't waste any part of the EMF on the other two elements. So, as the frequency increases, the circuit goes from capacitive to resistive and then to inductive. And at this particular frequency, when omega was omega naught, we have the highest possible value for the current, and therefore the power consumed by the resistor at that particular frequency will be maximum. We call this resonance. So this is a resonance curve, and here's the peak of resonance. Okay, resonance. This certainly is not the first time you heard this term resonance. It is of pivotal importance in our design of television and radio reception circuits. How do you receive a particular station, the signal from a particular station? We use a resonance circuit. Okay, when you buy a TV, you can tune the frequency of the receptive of the receiving circuits within a TV, so that it will match one of the broadcasting frequencies. Okay, the broadcasting frequency of a particular TV station. Then the signal from that station will be particularly enhanced, and the other signals will be suppressed. So you will get you will receive signal from that particular TV station. And if you change the resonance frequency to the frequency of another TV station, then you pick up that signal and suppress other signals. So basically, for a good receiver circuitry, you would hope for something like this. It goes up dramatically and it goes down dramatically. Okay, you have a very selective peak. So you see, when the frequency matches, you get an extremely high response, and the other frequencies you almost get zero response. All right, this type of curve is not as sharp as that, so it is not as selective as that. So it's not only going to respond to the resonance frequency. It's also going to respond a little bit to other frequencies. So if you want to just get a receiver circuitry for TV, this is a better curve than that. Okay, it's more selective. So that is the idea of how you use the phasor diagram to solve the LRC series. And the phasor diagram can also be applied in principle to any AC circuit with LRC in it that is powered by any sinusoidal EMF. But the series LRC is usually the one we study the most. And you can see the nice, using a vector diagram. And you can add vector graphically. You can see clearly the meaning of the phase difference, that sort of thing. Okay. Now, another issue we want to study. Okay. Another issue we want to study is the energy aspect of this problem. When you have an LRC circuit, you drive a current by the EMF. We know when the current passes through the resistor, no matter which direction it passes through the resistor always turns that electrical energy into heat, right? But what happens when you drive a current through the inductor or through the capacitor? Now what happens? Well, you know, when you do positive work to one of these elements, you're actually building energy to them, right? You can build electrical energy on the capacitor, and you can build magnetic energy on the inductor, right? My question is, after one cycle, okay, after one cycle, one period, how much energy is consumed by the resistor? We know the resistor always consumes energy. And is there any energy loss on a pure inductor or a pure capacitor? Okay, now your intuition probably tells you no. The inductor and the capacitor will not consume any energy, electromagnetic energy, right? But you can still drive a current through them. You still have to do work, right? So what kind of power do they deliver? Or what kind of power is delivered on the inductor, on the capacitor? How do we study the power consumption of an LRC series AC circuit? That is our next topic. Okay, so the power consumption and resonance, that's the next subject. When you start with Kirchhoff's rule, V equals VR plus VL plus VC, you can multiply each term with a current I. You get IV, IVR, IVL, and IVC. You know the product of the current and the voltage difference across an element is actually the power that it takes to drive a current through that element, you know. So this basically tells us the power delivered by the EMF, that's that, equals to the power delivered on the resistor, inductor, and capacitor combined. In other words, P equals PR plus PL plus PC. That's conservation of energy. Okay, what I want to do is to study each of them separately, PR, PL, and PC. Let's look at PR first. Okay, it is a function of the current. It goes like I squared times R. First of all, you know it's I squared. It's never negative, okay? It's always greater or equal to 0. And I itself is I maximum, I maximum, then sine omega t. So you go I maximum squared R sine squared omega t. And that, of course, varies from time to time. Okay, it can go go to as low as 0, can go as high as I maximum squared times R. Okay, this goes like I squared basically. My question is then, what is the time average power? Okay, what is the average value of the power consumption on the resistor? Time average. You know, in principle, this is what you should do. Okay, you take that quantity, you integrate over one period, so between any time t to one period big T later, and then you divide it by the period t. That is how we do it. So you have to do this integral. Okay, you have to do this integral, which of course I trust that you can easily do that. You know, you use double integral formula, whatever you can work it out, right? Now I want to show you something a little bit easier, something that's actually quite obvious if you think about it, because all you have to do really is to average the sine function. Okay, I maximum squared R, and then average value, the time average value of the sine squared function. That's what you have to do. Agree? You know, I don't really care what omega is. I don't really care what phi is. All I know is this, with this bar, I'm averaging this sine squared function over one whole period. Okay, over one whole period. And over that whole period, I can average the sine squared function. I can also average the cosine squared function. Now, even though sine squared and cosine squared generally are not equal to each other, you agree that when you average each term over a whole period, you should get the same value, right? So sine squared omega t minus phi should equal to cosine squared omega t minus phi if you take the time average, because the difference between sine and cosine is just, you shift, you know, just time shift them, right? It's not going to affect the time average. But wait a second, what if you add sine squared and cosine squared on? What do you get? You get 1, right? Okay, and yet they're equal to each other, time average. So what is the time average of each of them? No choice, 1/2. See that? So that they add them together, they equal to 1, and they're equal to each other at the same time. Okay, therefore I found that this time average is equal to 1/2, and I get PR average simply equals 1/2 I maximum squared R. Now, I can rewrite this as I maximum divided by the square root of 2, right? And then squared, and then times R. And this I maximum squared, I'm going to define what's called effective current. Effective. Okay, it's IEFF. IEFF, defined as I maximum over the square root of 2. Why do I define this as I effective? Because with this I effective, I can now rewrite PR average as simply I effective squared times R. Why is this a useful formula? Because in a DC case, when the current doesn't change, we say the power delivered by that current on the resistor is I squared times R, right? Now we have an AC circuit. The current actually alternates between negative I maximum to positive I maximum. The power also changes all the time. We're interested in the time average value of the power. So, it turns out if you do all this, you find it's, it's equal to 1/2 I maximum squared times R. But people tend to forget that, right? People tend to forget that. And the question is it possible I can introduce an effective current so that with that effective current, I can calculate the average power delivered by an AC circuit without considering the time averaging, without worrying about this 1/2. So, in other words, with I effective introduced here, the average power in an AC circuit going through a resistor is the same as the power delivered by a current I effective over a DC circuit, okay, going through the same resistor. That way we can treat this AC circuit effectively as if it were a DC circuit as far as calculated average power is concerned. I don't have to worry about maximum minimum value, 1/2, whatever. Just use I effective. Okay, just use I effective. As a matter of fact, you can also rewrite this as V effective squared over R. And this V effective, as you probably suspected, is just V maximum over the square root of 2, just like that. Okay, just like that. And with this V effective value, if I told you the V effective value directly, then you can calculate the time average power delivered by that V simply by using V effective squared over R, as if it were just a DC circuit with the same constant voltage of V effective. Okay, now we always say that the power outlet that we use here is 110 volts, right? That 110 volts, do you suppose it is the peak value or the effective value? Well, when people calculate the power consumption of a device hooked up to the power outlet, do they worry about instantaneous power? I don't think they do, because it varies 60 times a second. I don't think anybody's dumb enough to actually care about the instantaneous value. You care about the instantaneous value, right? I'm sorry, the time average value, right? But as far as time average value is concerned, you really have to take the peak value and divide it by 2. You really have to do that, right? You have to do that. But few people would notice that. So it's much easier if they simply told you V effective, because that way you don't have to worry about this 1/2. You simply take that V effective squared and divide it by R. So that 110 volts really is what? Is the effective value of the EMF that's delivered through the power grid. What is the actual peak value? What is Vm? Vm really is square root of 2 times V effective. Okay? In the case of the AC power grid here we use in this country, V effective is 110 volts times the square root of 2. You get actually about 171 volts. Okay? That is the peak value. Okay? The maximum value, not 110 volts. Okay, so that was a discussion about the power consumed by the resistor. Now, as far as the power consumed on the capacitor and inductor, things will get more interesting, because when we take the product of I and VR, you notice I and VR have the same phase. But I and VL, they're out of phase by 90 degrees. So is I and VC. So when one of them is a sine function, the other one is a cosine function. And we take the product of a sine and cosine. Okay? You may not always get a positive value, right? You may get negative values, as a matter of fact. And what happens when P is negative? When P is positive, such as always is the case for the resistor takes electrical energy and consumes it, right? When P is negative, such as sometimes happens to PL and PC, to L and C, then that means this element, the L, the inductor and capacitor, at that moment is not consuming energy, is not taking energy in. Rather, it's what? It's giving energy back into the circuit. Okay, so this is something new which we'll study in our next part.